So in this video, we're going to talk about how to divide radical expressions, expressions that have radicals in them. One of the things that we're going to look for you to do is to do a process called rationalizing the denominator. That comes from the word rational number, right? So rationalizing the denominator, that means that we want our denominator in our fraction to not have any radicals in it. Okay, we want the denominator with no radicals. So we want the denominator to be an integer, and integers are part of a set of numbers called the rational numbers, and those are numbers that can be written as fractions, as ratios of two integers, right? So by rationalizing the denominator, that's where the word rationalizing comes. So we want our denominator to be an integer. So let's take a look at a couple of these. The first example we've got here is a fraction says 7 divided by square root of 2. And so square root of 2, we want to be able to convert this fraction to a fraction that has no square root in the denominator. And the way to get rid of a square root is to have a perfect square in the denominator, right? Because if we take the square root of a perfect square, then that gives us an integer. So we're going to try to convert that square root of 2. That 2, we need to put a perfect square here. So one of the things that you may want to have handy as you do these problems is a list of squares. So let's just make a quick one here. Let's see, let's make a list of squares. Oh, let's go to 12. How's that? Okay, maybe 10. Okay, maybe 11. Okay. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. So I know you know these, but let's keep these handy. We'll use them today, okay, on this video. And these are the perfect squares on this column. And so we're trying to change a 2 to one of these squares, the smallest one you can get to. And so the smallest one that we can get to here is 4, right? It'll be pretty easy to change a 2 to a 4 by multiplication. So what we're going to do to rationalize this denominator, let me rewrite here, is that we're going to multiply the denominator and the numerator by the same radical that will get us a perfect square under here. And we decided that perfect square is going to be 4, so we need another 2, don't we? 2 times 2 is 4. Of course, anything that we do to the denominator, we have to do to the numerator to keep this fraction equivalent. So that's why you see me multiplying here both of these by the square root of 2. So on the numerator, we have 7 square root of 2. As you know, we can multiply terms that have radicals. They don't have to be like radicals. And under here, the square root of 2 times another square root of 2 is the square root of 4, which simplifies to a 2. And now our denominator is an integer, and so it's a rational number. And so we have done the task. The task was to rationalize the denominator. So let's go to this next problem. Now we have 24 divided by square root of 6. Once again, we are trying to get a perfect square under this square root here. So I'm going to come over here to my list of squares and go for the smallest square that I can turn that 6 into, and that 36 is looking good, right? So that means that we're going to need to multiply our numerator and our denominator by another square root of 6 to make an equivalent fraction. And so that gives us 24 square root of 6 over the square root of 36, which is 24 square root of 6 over 6. The square root of 36 is 6. We're not done, because did you notice that there's some simplifying we can do here. We can reduce these. And so 6 divided into 24 is 4. So 4 square root of 6 is my simplified fraction. Okay, we have square root of 8 divided by the square root of 5. So again, It's the denominator we're looking at. That's the one that's the problem. We want to rationalize the denominator, so we need to turn this square root of 5 to a perfect square under the radical. And as I look again at my list, I'm looking at my list. Yep, that 25. So we are going to multiply by root 5. Anything we do to the denominator, we do to the numerator. And now we multiply across, and we multiply under these two radicals. Here we get square root of 40 over, and then here we get square root of 25. Or by now, are you getting the idea? If you have two square root of 5s, that we're going to get the 5, right? Square root of 25 is 5. We can start doing this in our heads. But now look at this square root of 40. We're not done. Can you see the perfect square in there? You want to simplify. You want to simplify here. And so 40 is 4, square root of 4 times the square root of 10, right? And the square root of 4 is 2. So we have 2 square root of 10 over 5. And that's now our simplified answer. All right, we're over here at square root of 10 divided by square root of 12. We want to change that 12 to a perfect square. Let's go back to our list over here. Okay, what's the smallest perfect square that we can turn 12 into? And look at here. Did you think of 36? Because that would be small. Now, sometimes my students want to go all the way to 144 to rationalize this denominator here. But the 36, that's smaller, easier to handle. So we're going to multiply by 3. We need this to be square root of 36 here, right? Now I have square root of 30 over square root of 36. And that's going to be square root of 30 over 6. And that's in lowest terms because 30 doesn't have a perfect square in it, right? So we are done. Now, that's one way to do this problem. Method 1, right? But here's a different way. If you notice, when you have a fraction and the numerator and the denominator are under the same, that they both have radicals, you are allowed to put one big radical and then reduce the fraction like this. So 10/12 reduces to 5/6, doesn't it? And so now I can go back and switch those out. See what I did? And now it's very clear, the 36 now, isn't it? Can you see the 36 there? It's very clear that we can turn that. We need another 6 here now, and we get the same answer, square root of 30 over 6. So there's another method for problem number 4.